So friends, on behalf of the Center of Excellence in Advanced Manufacturing Technology, I would like to welcome you today's webinar. Today is the 30th week. As you know that we have started our journey sometime in the month of March, and we do have discussions on different topics in the field of advanced manufacturing, smart manufacturing, robotics, additive manufacturing, human robot collaboration. Today is also we are going to listen one such topic. You know, we talk about the industry 4.0. We are landing up in the digital era. We are using AI ML like anything in the manufacturing domain to get the more visibility about the process, so that we can make the the manufacturing process more smart, more smart. But at the same time, we are also thinking that we have to go beyond artificial intelligence. How the combination or the collaboration between human and the robot can be made together, so that it can bring more visibility, more cognizance, and having better cognizance in the machine will be smarter enough to tackle the unforeseen situation. That's the objective. We would like to make the manufacturing, the system more flexible. Today we have moved from the automated system to the autonomous systems, but it has to be more and more flexible. So we are very fortunate to have one of the eminent, the speakers in this, the researchers in this field. I'll introduce Professor Vaibhav Srivastava. Professor Srivastava received his BTech degree from IIT Bombay in 2007, MS degree in Mechanical Engineering 2011, MA degree in Statistics 2012, and PhD degree in Mechanical Engineering 2012 from the University of California, Santa Barbara. Professor Srivastava is currently a faculty member in the Electrical and Computer Engineering in Michigan State University. He's also affiliated with Mechanical Engineering, Cognitive Science Program, and Connected and Autonomous Network Vehicles for Active Safety, which is abbreviated as CANVAS. He served as a lecturer with the Mechanical and Aerospace Engineering Department of Princeton University from 2013 to 2016. He serves as the IEEE Control Systems Society Conference Editorial Board since 2018. He has received Best Paper Award at the 2014 European Control Conference, which is one of the prestigious conferences in the field of control engineering. His research focuses on cyber physical and human systems, with emphasis on mixed human-robot systems. As I mentioned, that we talk about the cyber physical system and all. Now, cyber physical and human systems is also, it's a mixed. The combination is coming up to have the better visibility. So, Professor Srivastava, it's now up to, I'm requesting you to just start your talk.
Okay, assuming everything is working well.
Yeah.
Okay. Right, thank you, Professor Pal, for such a nice introduction. It is really a pleasure to be speaking today at this talk series. And thank you, everyone. I mean, I know it's 8:30 on a Saturday evening, fairly late. So thank you for taking the time and coming over to listen to the talk. As Professor Paul suggested, I'm going to talk about shared human automated systems. And what I want to bring to table today is the impact of the modeling of the human, and some approaches that we have experienced have been useful in terms of understanding human behavior. And then I will talk about, once we understand what are the expertise of human, and humans are not expert in everything, right? Whenever we talk about human behavior, there'll be some things which will be really nice, and there'll be some things which should not be at the level where we want them to be. So how do we kind of design strategies that can identify human expertise while mitigate their shortcomings, right? And once we have those things, how do we synergistically design a system such that we can have efficient performance, right? So I'm going to focus primarily today on supervisory control, where human is providing some sort of high-level input to the system. And towards the end, I'll briefly touch upon some of the recent efforts that we have been taking through, where there is a more sort of real-time collaboration between humans and robots. But today's talk will primarily be focused on supervisory control applications. So uh, so here is the vision of shared autonomy and cognitive modeling. So we think about humans and robots working together. Now there's a term that comes up which is called co-robot, which stands for collaborative robot. So we have a lot of sensors deployed. There are camera networks all over the places at multiple places. And there's a lot of information available there, right? And there's a human, and you don't want in a supervisory control application, we are thinking about human making decisions based on all the information that is available to them. And sometimes we want to take human input and implement that on a robotic system. So the vision is that you don't want human to directly interact with that multi because it's too much information to handle, right? So you want to design a collaborative robot which is going to parse the information that is available here and present something in a form that the humans can process easily, or suggest to human how to operate so that they operate in a good cognitive state. And the other part is when you get a high level human input, how do I use that high level input to implement in, for example, in a robotic network or on a single robot, right? So what we think about shared autonomy, it is a technology that brings the memory and computational power of the machines with the cognitive abilities of the humans, right? Our goal is to mitigate the inefficiencies of humans, but leverage the abilities that they bring to the table, right? So the question that we are asking is, how should we best integrate human input into autonomous algorithms? How do we support humans by designing aids that can assist their decision making? So sometimes it's called decision support systems, right? If you think about the areas where this is applicable, you can think about environmental monitoring. There's a lot of places where AI is great, but sometimes it doesn't work. So I can give an example. Some of the experiments we have done with searching victims. I take the state-of-the-art machine learning algorithm and I show a human victim to him. It identifies it as an aeroplane, right? So that happens. So if you have really cluttered environment and you have uh, you have an algorithm in which the picture is not very clean, it may very well identify human as an aeroplane, and that's not something you want, right? So that's where you need, especially when you're talking about safety critical applications, a requirement of human in the loop is really important, right? And then you can think of in healthcare, people are thinking about robots doing surgery and things like that. So in those domains, especially in manufacturing, this is a talk focus on manufacturing. A lot of work has been going on in terms of collaborative robots that don't work in isolation with humans, but they work alongside with humans, right? So defense, a lot of applications, I think, in defense where humans and robots work together. Agriculture, towards the end, I'll talk about. I mean, there's an overall shortage of people who are doing agriculture. The demand of food is rising continuously, and there's a shortage of land that is used for agriculture. And everywhere in the world, there are more and more people who are going to the urban areas, and there are lesser and lesser people doing agriculture. So demand is rising, and the people are going down, land is going down. So we have to learn to do agriculture in a more efficient way. And robotics is one way to do it, right? We can do things, we can detect things, we can design optimal policies to do agriculture. But at the same time, as we are doing it, we need some human supervision, right? So we need to design these systems such that a farmer can use it, right? A trained engineer being able to use robots, that's not our goal. Our goal is to make sure that a farmer can go and buy a robot from a shop and use it, right? That is the level of understanding we want to go to. And once I buy it, I need to be, the robot should be reliable. I should understand what it can do, what it cannot do. And those issues in literature are called are kind of dubbed into a single term called trust, right? So how do we care about this trust of human in robot, right? So those are the places where all these things will come into the picture. Uh, so now I'm going to talk about, so this is kind of in the supervisory control, kind of the things that I have been thinking about for many years. So you can think about this is mostly a search and surveillance problem. So you can think about some victims that are lost in wilderness, or there's some other kind of search that we're trying to do. So you have some sort of robots that have been deployed, and they collect, for example, imageries and or other sensory information, and you have this incoming task, and there's this a realization of what I call a collab co-robot. Now, it need not be a co-robot, need not be a physical moving object. It could be just a machine which assists in decision making, right? So let's look at the pieces that are here. So here I have a decision support system, right? That is going to parse all this information and suggest, give it to the human to process it, right? And this could be also making recommendation to human that, okay, I mean, there's too much to going on, there's too much to do, so you perhaps want to do things quickly, while don't spend too much time on details, because there are literally too many things to do. And maybe if the load is not high, it may say, okay, there's not enough load, you can spend as much time as you want, right? The other part here is algorithms for automation, right? So there's a piece that is coming in here, the information that I get from here, I get the human operator's input, and I need to learn to integrate the machine output, the sensory output, with the input from the human. And how do I integrate that data? And that should inform my algorithms for the automation. That should change the policy with which I am going to implement a robotic system. And then the piece that comes in here, the task that goes in here, some sort of recommendation that goes into here, and I get operator decisions. I need some sort of model of human to really understand the quality of decisions they are making, to really understand what are the expertise and what are the shortcomings of the human. So a big piece comes in here which talks about cognitive models for the humans, right? Sometimes we can work with behavioral models, and most of the times we work with behavioral models. Sometimes we may have access to things like EEG or GSR data, and then we may be looking at some sort of more sort of cognitive model there. But most of the times we can just work with behavioral models for the humans. Okay, so that is the piece, and I think a lot of my work deals with pretty much all the bullets here. I have a lot of work on with I've collaborated quite a bit with neuroscientists to really develop cognitive models for humans. I'll briefly touch upon some of the things we have been doing with decision support system. I would not touch at all on the algorithms for automation. I think I have been doing work with decision making under uncertainty in network systems, which I would not be touching on. Most of the today's talk would actually be focused on this piece here, which is decision integration. How do I integrate humans input, or in fact, any general input from multiple sensory modalities, and integrate that into the robotic system, right? So I'll start by very briefly touch upon, since it's relatively old work, so I'm not going to spend too much time on it, but I want to briefly touch upon what do we do by when we have to model human decision making, right? And I won't go into too much detail, but I want to touch upon to really show how can we identify the expertise and shortcomings of humans, right? And that is really important when I design algorithms, because I have some input from human. The moment I realize what is good, what is bad in that input, then I can design my algorithms to really account for those good things and bad things. Okay, so there's this task called multi-bandit task. So in multi-bandit task, you are given n options. Each option has some unknown mean mi. And each time I go and select that option, I obtain a reward that is corrupted by noise. And for now, let's assume that reward is corrupted by a Gaussian noise with known variance sigma s squared. My option is that I can only play one option at a time, right? And what I want to do is I want to maximize my expected cumulative reward until time t, right? So this is a prototypical problem, which is called explore versus exploit trade-off. I need to explore, I need to play all the options so that I can know what is the underlying reward mi. But at the same time, if I just keep on exploring to learn the reward, my total reward would not be high. right? So I need to learn enough so that I know which is the best option, and then I need to exploit because I need to maximize my reward, right? So this is a problem that happens in robotics. Whenever I do environmental monitoring, if I have to go and search for a source of oil spill, I get very noisy information. I have to solve this problem, right? Because I don't know where the source of oil spill is, uh, but I'm getting uncertain data. I need to make that reliable to make sure that I'm getting towards the source, right? So we wanted to understand that how do humans fare in this kind of task, right? So here's an example of what we can be modeled as a multi-amended task. So this is an example of inspecting a ship hull. So here is a hovering underwater vehicle, and it has some sort of sonar data collected, which can go and see the ship hull. And each time I'm only looking at one particular point on the ship hull. So I can play, that is like playing one particular option. And I get some noisy data, and from that I want to figure out where are all the places on the ship hull which have defects, right? So it's a very nice application of non-destructive evaluation done through a robot. Similarly, for the oil spill case, when I go and sample at a particular point, I can say what is the intensity of oil spill there, and I can move around and try to find the source which has the maximum uncertainty, maximum intensity of this spillage. So one key feature that happens in this is there is this mean reward surface. And unlike a standard multi-arm mandate problem where each of these arms may have rewards which are independent of each other, we get some sort of correlation structure, right? So to do that, what we did, we said, okay, let's spatially embed these multi-arm mandate problems. So you still have rewards at each arm, you get a reward surface. Now we assume that these rewards are correlated, and depending on how much correlated they are, you will change the smoothness of the surface, right? So we have a model in which the covariance is modeled by some parameter sigma 0, and there's a length scale parameter called lambda, and dij is the distance between points I and point j. Okay, so for this kind of thing, once I go and sample a particular point, there's a very nice Bayesian inference that one can write. If t is the point that I sample at time t, rt is the reward that I obtain. There's a very clean Bayesian inference that one can write down what will be the posterior mean and what will be the posterior variance. And once you have this, there is an algorithm that I can write down, which is of this form. At each time, this is called sometimes indexing rule. I compute my posterior, and at each point I compute what is called 1 minus kt upper credible set, upper credible limit, which essentially means that I have some sort of term which accounts for posterior mean. This is my posterior variance of posterior standard deviation, and I have some term which is putting some time varying weight on that. So this means exploit. That means try and go to sample point which has maximum posterior variance. This one is explode, which is trying to say, I have a lot of uncertainty in the world. Let's try to go and reduce that uncertainty, right? And this weighing is kind of a optimal way of putting that weight on these two terms, which is changing with time. And for this policy, we were able to show that we will achieve very close to optimal performance, right? Now, in cognitive modeling, a very common strategy is to say, okay, let's start with what would be an optimal policy. And then people talk about there are cognitive limitations in the humans, right? And to account for that, you will change something in the optimal policy, right? So a traditional approach is that you kind of introduce some sort of noise in that. Of late, people have started to do with the search in deep neural network and things like that. People have started to say, okay, let's go to deep neural network, which is going to do optimal thing, and add some constraints which would account for cognitive limitations, right? Since this work is much before deep neural network was popular, so we did what was more traditional. That instead of picking the option of the maximum value of qi, we will pick that with a probability, and we change the this is sometimes called a softmax way of picking the optimal action. So if you look at this model, so this is what we call stochastic useful model, and we thought that okay, this would be a good model for human. There was a lot of literature. What are the features of human decision making? We were able to capture pretty much all of them in this model. So you think about it, sometimes people talk about exploration as having two connotations for human. This one that you see here, this is called a directed exploration. I have an option which is very uncertain, and I am specifically directing my actions to reduce uncertainty, right? And sometimes people call this random exploration because I am randomly choosing whatever option. It's an outcome of a probability distribution. So this is sometimes called random exploration, right? So these are called two different modes of exploration for humans. But nevertheless, what it means that we have a model in which we have 4 parameters. You start with some initial prior on the mean rewards. You have a length scale parameter, you have initial sigma 0, and you have some sort of a V term that comes in this noise model here. So with this model, we did some experiments with Amazon Mechanical Turk. If I remember correctly, we had around 300 subjects data. And we looked at what is called regret. Regret means what is the gap between the optimal performance and the performance that I get, right? And in that case, we were able to divide the trajectories that we get into 3 clusters. There was one set in which we were getting really good performance. There were some subjects which were really bad performance, that is a blue one, and there were some subjects which were doing some intermediate performance, right? Now we went ahead and tried to estimate these parameters. And what we realized that if you look at the subjects who were getting good performance, they had a very good estimate of this length scale parameter lambda, even though their means and variances were really off. They were very noisy, but the only thing that they were doing really well was this length scale parameter. Now, length scale parameter really corresponds to identifying patterns in a structure. That means I'm saying things are more correlated, things are less correlated. So if the nature of continuity is known to me, I know that things are good here. So neighborhood things will be very similar. And so I should go and search at other places which are far off, right? So the takeaway message from all this modeling is that experts identify patterns well. The beliefs may be off. They may not be able to tell you the exact mean at this point is going to be 100. They may be able to say, okay, if the mean is high here, it should be high in the neighboring regions as well. And maybe if you do some exploration, you may be able to find what exact mean is, right? So this is a key point that I want to take forward from here, that experts identify patterns well. Their true estimates may be off, but we can rely on them to provide us very good estimates of the patterns that exist in the environment. Okay, so now with this basic understanding of human subjects, what I want to do, I want to go ahead and talk about a search framework in which we can account for this human behavior. And in general, this is a much broader framework. It can not just account for humans, it can also account for sensory data from multiple modalities. So here is a search problem. I have a robot that is equipped with a downward facing camera, and it is moving a 3-dimensional space. There are unknown number of targets that might be present on the floor of the ocean bed, or this could be aerial environment where they're just on the ground, that's fine. And there's a computer vision algorithm which can detect the human, and it can provide a score, what's a likely event that this person is a victim. And my goal is to identify all the targets. Okay, sorry about that. Okay, my goal is to identify all the targets as quickly as possible with a desired accuracy. Okay, so I think this problem has been studied in literature for quite some time. People to how to search an environment in a nice way. Something that people have not explored really, how to leverage the 3-dimensional aspect of an environment. People just think about a robot moving in a plane, but can we leverage that we can move up and down? And this is something that people have not explored that we started to look into. And the idea really is, it works really well. So the idea is very simple. If I have a drone or a underwater vehicle, which can see things from the top, it can perhaps will have very low accuracy in terms of detection, but I can very quickly rule out the regions where there's nothing. And then I can only focus my attention on the regions where there's something interesting, and then I can go here and achieve the desired accuracy, right? But how to do that systematically in an algorithmic way for which we can prove certain desired accuracy? So that's what we are going to talk about. So we call it a multi-fidelity framework. So the idea is really simple. As I said, if you see things from a very high altitude, you have wide field of view. You can see many things. The accuracy is low, but we can eliminate uninteresting regions very quickly. And as I go down, I can as I go down, I can do very accurate detection, but my information would be less correlated, and my field of view is narrow. So the correlations are high because, see, if I go to two neighboring points, I'm seeing pretty much the same region from both the locations. So there's a lot of overlap in the imagery, which means that I have more correlations between the two neighboring information. As I go down, the lesser overlap between the imagery that I get, that means the correlation is going to be smaller. So we went ahead and looked into what is called a multi-fidelity Gaussian process sensing model. So the way it works is following. So let's say from the top location, when I see, I get some sort of sensory information, and that looks like a realization of a Gaussian process. Let's call that H1 of X. As I go down, what happens? I start to get better fidelity information, right? So I am going to modify my sensing function by an additional input H2. As I go further down, I get more higher fidelity information that is going to modify my function as H3. And together, that gives me F3, right? So this is called multi-fidelity model. So I start with an autoregressive sensing model. At the highest fidelity, my output is the realization of a Gaussian process. Let's call that H1. As I go to a deeper level, I get better information. So I have the original F1. I do a scaling of that, and then a bias term to that. Now, this bias is, you can think about, as I said earlier, the human input can provide us very good information in terms of correlations, but they are biased. So think of this, F1 is capturing that correlation very well, but H2 is the bias term that I'm explicitly modeling. Okay, and I can keep on doing that. I'm assuming at the highest fidelity level, I am able to get the. Okay, so for this model, as I said, one of the fidelity levels could be humans. It could be like H1 is by the human, which has very nice correlation information, but there's a bias which I'm accounting for in the model. Okay, so now I'm going to, mostly for the purposes of the analysis of this algorithm, I'm going to assume if there's no target present, my machine learning algorithm is going to give a output score which is less than threshold. So for example, we are using the algorithm called YOLO. You only look once, and the score is 0, for example, here. And when there's a victim present, the score is 0.76. So we're going to assume that the score is less than threshold when there's no target, and when there's a target present, the score is going to be more than threshold plus some sort of delta. Now, this delta is a measure of how easy or difficult the scene is. The larger the delta, that means it is easier for me to detect a victim. The smaller the delta, that means the image with a target or without a target look pretty much similar, and it is more difficult for me to do it. Okay, so my goal is to really minimize the time to search all the victims, and I don't know the number of the victims, and subject to a constraint on false alarm. That means if there is no target present, I must not declare that there's a target, and the probability to do that. And a misdetection constraint, that means if there is a target, I must not miss it, and the probability with which I miss it must be smaller than delta, right? So these are called error tolerances. So given that these two constraints, how do I do it? So here's the algorithm that we have. It operates in a epoch structure. So let's go one by one here. So the first part here is sampling and fidelity problem. What does it do? It determines at what points in the space must I sample, and fidelity tells me at what fidelity I should sample, right? So fidelity, you can think of the height at which I'm going to sample, the altitude at which I sample from. So sampling locations and fidelity planners, I can do it in an epoch-based structure. So I can do it in a way that I'm going to reduce uncertainty by a certain amount, and I can compute what are the points I should sample to do that. And then I can compute a traveling salesperson tour, because that is the smallest distance I will travel to travel those points. So here's an example. So we go and sample most uncertain points until the uncertainty is below a threshold. And then we keep on decreasing this threshold geometrically as a function of epochs. And then I'm going to compute a TSP tour through sampling points. So this is in my first epoch. I am sampling at the lowest fidelity. That means at the highest altitude, I determine these points. And once I have done that, what I do, I go to the inference and Bayesian classification algorithm. I compute the posterior distribution of a target being present. And then I do a Bayesian classification in terms of what are the regions. So if you see this figure, this red is high likelihood there is a victim present. Green means there's a lot of uncertainty. Blue means there's pretty much no target there, right? So once I have done that, the next step that I do region elimination. In region elimination, wherever I'm certain that there's no target present, I'm going to eliminate that region from further exploration. And this is really where the multi-fidelity aspect comes into the picture. I am very quickly eliminating the regions where there is nothing interesting. That reduces my search area, and that is going to reduce my search time significantly. So as you can see here, the green dots, so the epoch 2 has started. Do the same exact points, go to the most uncertain point, reduce the uncertainty below threshold. So here greens one are the one that I'm picking at the highest altitude, and red ones are at the lower altitude, higher fidelity information. And the switching is just a little bit more involved here, so I'm not going to go into detail, but it really depends on how much uncertainty remains in the environment. Based on that, we have a rule that allows us to switch from higher fidelity to lower fidelity to higher fidelity. Once we have done that, we again repeat the same process. We do the Bayesian classification, end of epoch 2. I have reduced the uncertain set. I've increased the set with no victim to a larger set, and I have the sets with targets and uncertainty much smaller. We do one more round, and then we achieve the desired accuracy, and we are able to say it looks like there are 3 victims in the environment. Okay, so here's an illustration of this in gazebo. So this is a underwater environment. We place in some victims there. So this is the first time it is doing the sampling at the highest altitude. And once it finishes sampling in that environment, it is going to update the occupancy map, eliminate interesting regions. So all these are eliminated. Now the second epoch starts. You can see that it is still doing the green ones, and at some point in time, it will switch to a higher fidelity. So you can see the field of view is going to change. Now you're going to see a very different view. So you're looking at much closer. And once you're done with that, you'll again update the map, eliminate regions, and so now we have uncertainty set which have been further reduced. And in the last epoch, I will do that. And then my desired accuracy was less than 1%. So 99.3% is the accuracy here. And that's where we stop, right? And we can do very formal analysis of this thing. So for the classification strategy in the EMTS algorithm, for any location X is misclassified with probability at most equal to delta. And the other result that we can establish is what is the time that I need to search through the environment. So it is proportional to 1 over delta square, log 1 over delta. So in terms of theory, log 1 over delta is the best you can do. I mean, there's a rich literature on learning and environment. And if you want delta accuracy, log of 1 over delta is the best thing that you can do. In terms of delta, 1 over delta square is an optimal dependence. Log 1 over delta is an extra term which we were not able to get rid of. But if you think about it, is coming in as log of delta. So if delta is really small, log delta is not going to increase a lot, right? Log delta is a very slowly varying function, so it is not that big a concern. But it would be very nice if we were able to get rid of log 1 over delta as well. But since log is not it is a slowly varying function, so it is okay in terms of performance, but yeah, it is one of those things where you theoretically you want to get to the optimal level, but it becomes difficult when practically it's not a problem. But so that was the results that we were able to establish here. How am I doing on time? Still have 25 minutes, right? Yeah. Do I have 25 minutes or I have 15 minutes?
No, no, don't worry. Please go ahead. Yeah, it's very interesting. I'm trying to find out its application in the manufacturing. Please go ahead. Yeah.
Okay. All right. Thank you. All right. So far, what I talked about is talking about this for a single robot, right? So now I want to talk about how do I take the single robot policy and extend that to multiple robots, right? So this problem has been studied in the context of controls. It's called coverage control problem, and the idea is that you have an environment and you have some sort of demand function. In this case, it's a sensory function. What's the likelihood of the victims are present in these areas? And you want to partition this environment into, if you have, let's say, in this case, 5 robots into 5 regions. And if you can partition this environment well, then you can take your single robot policy and implement it to each of the partitions, right? So this is called equitable partition, and we want to allocate 1 robot to each partition. So uh, so we have environment D, and now my problem is that the standard coverage control says if I know the demand function or the sensory function, I can allocate robots to each of those things. I can partition things. My problem is I don't know where the victims are or what their likelihoods are. So it's an unknown sensory function. And I want to deploy these things. And typically what is done, you want to minimize what is called a coverage loss. So let's try to understand what does coverage loss means here. So Q is a location of Q is any specific point in the environment. Eta I is the location of the robot I. So I want, and phi Q is kind of the demand of a robot's processing at point Q. So I'm looking at the distance of a point from Q, how much robot is needed there, and I'm going to integrate that over the partition of in which the robot is deployed. So this is kind of measuring how far the robot is from a desired point where and a desire of the robot at that point. And I'm going to integrate it over all the environment over each partition and sum that over all the partitions, right? So this kind of measure of coverage loss, that means if the robot is needed, if phi is the need of a robot at a particular point Q, how far the robot is located from that particular point, and you look at the square distance, you weight that by that importance functions or the demand function, and you basically add up over all the points, right? So that is called a coverage function, and there's a lot of literature out there. So here's an illustration of what that coverage functions look like. So if this is the demand function, so you can see things are high here, things are low here, and suppose robots are deployed in this particular fashion. So you can see that most of the demand is here, and my robots are really far off, right? So this is a bad performance function. This is a bad deployment. This is a good deployment here. I have robots. Most of them are focused near the points where the demand is high. And even though there is small demand here, so this robot is deployed far, but the area that it has is much larger because there's very small demand in this area, right? So the solution to this kind of problem is sometimes called what is called a centroidal Voronoi partition. So Voronoi partition has 2 elements to it. So one part is Voronoi partition. Voronoi partition means I take an environment and I am going to deploy my robots eta I and eta j in a way such that if I look at any point in this partition, for example, any point which is closer to this robot compared with robot number 2 here, that would be in the partition of this robot, right? So let's call this robot 1, let's call this robot 2. So any point which is closer to robot 2 in comparison with robot 2 must be in the partition of robot 1. Okay, so that is Voronoi partition. So both of these partitions that we see here are Voronoi partitions. So all the points which are closer to this robot are in the partition of this robot. But there's another part that comes in here, which is called centroidal Voronoi partitions, which means that in a Voronoi partition, if I look at the centroid of each cell, the robot must be located at that centroid, right? So if I look at the first partition here, depending on the weights that are here, you can see that if I look at this partition, the centroid would be somewhere here. For this partition, the centroid would be somewhere here. For this partition, centroid would be here. And the robot is not located at the centroid, right? So I had the robot positions. Based on those positions, I generated the partition, and that partition is such that robot is not located at the centroid. But if you look at on the right hand side, if I look at this guy, this is the Voronoi partition. My robot is located at the centroid. It is located at the centroid. It is located at the centroid. It is located at the centroid. Right? So that is what we call the centroidal Voronoi partition. So if I give the robot configurations ATAs and I generate a Voronoi partition, if it happens that for that centroidal partition, if I compute the centroids of that Voronoi partitions, they are also located at eta I, then I call it a centroidal Voronoi partition. And there is the algorithm that can do it very well. It is called Lloyd's algorithm. And it is very simple. You start with some locations eta I to eta k. And given to me each locations, I can compute the Voronoi partition, which essentially says that, okay, let's go and identify all the points which are closer to me compared with other robots. And then I'll compute the centroids of each partition VI, and then I move to those centroids, right? So here is how I start. So you can see the robots are deployed here. They have a Voronoi partition. For each of these Voronoi partitions, I will compute the centroid locations. I'll move to the centroids. Once I move to the centroid, I will recompute the Voronoi partition. And as we keep on doing this, I'll eventually converge to what is called a centroidal Voronoi partition. Right? So in this process, what is required here that I need to compute the centroid, and to compute the centroids, I need to measure the demand function. Right? If I don't know the demand function, I cannot compute the centroids. Right? So that is what we want to address here. Because in the example of search that I gave you, I may not know these likelihood functions where the victims are. So if I don't know the demand function, how do I address that? So I want to do that. So the sensory function, again, I'm going to model it as a Gaussian process. And each time a robot is at location X, it measures the demand function with some Gaussian noise. It has a flavor of that multi-arm bandit problem where I started with, but instead of picking an option each time which has highest reward, I'm trying to converge to a configuration which provides me good coverage. So again, the same explore versus exploit trade-off appears here. Robot must go to the centroidal Voronoi configuration to provide good coverage, but it must deviate from centroidal Voronoi partition because it needs to learn the environment. If it cannot learn the environment, it cannot go to a good environmental centroidal configuration. Right? So there is this similar trade-off as we saw in multi-arm bandit problem appears here. So how do I handle that? So the first question I'm asking is, how can I even characterize this explore exploit trade-off, right? So people have tried to define this this trade-off using a notion of regret, and I think all the things that I'm going to talk about, if I say that my the biggest contribution that we have made to this literature is really defining a appropriate notion of regret. So the coverage problems are traditionally considered very hard problems because these are non-convex optimization problems. You pretty much don't have any algorithm that will converge to the global optimum. All the algorithms that exist out there, they converge to local optimum, and each of the local optimum is a centroidal Voronoi partition, and it is kind of assumed that that is efficient, and usually it is very good. Now, people have tried to address this notion of regret for coverage problem, but they always defined this regret with respect to the global optimum, right? Now, the problem is that the algorithms that exist even in the setting where I know the demand function, I never converge to global optimum, right? So if I define performance measure, which is with respect to that global optimum, I'm never going to do really well unless I make some really some assumptions which are very hard to satisfy in real setups. So we instead came up with a new notion of regret, which we defined coverage regret, and we defined regret as the distance of a configuration from what would be a centroidal Voronoi partition. So here I define a loss function. So at a given time, my robots are located at locations eta t, and associated partition is p of t. So I look at the difference between the loss function that I get at the current configuration from what would have been the centroidal partition? So if I replace my robot configuration with respect to the centroids for a given partition, so that is my first difference. And second difference here is, if I am at eta t and pt, what would be the loss if I replace my current partition with respect to the Voronoi partition with respect to the original weight functions, right? So whenever I'm computing these guys, I'm using the original weight functions, and when I'm computing these guys here, I'm using my estimates. So if I'm converging to a Voronoi partition, centroidal Voronoi partition, both of these terms are zero, even if I am using a local optimum, right? So this regret turns out really well, and it captures pretty much all the algorithms, all the state-of-the-art algorithms we could use in coverage control. This is really well defined for those problems. So I think with this notion of regret, we were able to analyze this problem. So we came up with this algorithm which has the following structure. So it operates in epochs, and each epoch has different phases, which we call estimation, information propagation, and coverage. So in estimation, we are more sort of exploration phase. We are just going to the most uncertain point, try to reduce the uncertainty below a threshold. Then, because it's a multi-robot problem, we have a small duration where we transmit data. We could do a consensus algorithm or some other kind of distributed algorithms to really get onto the same page. And then we just simply go and implement one of the standard coverage algorithms, right? So in the estimation phase, I want to reduce my variance, again, just like the search problem, geometrically after each epoch. We find all the points, we compute a TSP tour, we collect samples, and then I go on to this problem, which is information propagation. We can pick whatever favorite algorithm we like. We can do flooding, we can do cloud-based information sharing, we can do finite time consensus, and based on that information, I can compute the posterior mean. And then based on that posterior mean, I'm going to implement my coverage algorithm for an exponential amount of time, right? Once I do that, so let's see how the plots will look like. I start with some initial estimates, and we are doing this TSP tours, and these are my initial partitions. And you can see this is instantaneous regret with respect to the best that we can do and what we are doing, and the cumulative regret, right? And whenever we have cumulative regret saturating, that's a good sign, because a saturating regret means that I'm learning the environment well, and the more saturated it is getting, that means I am learning the environment really fast. So we get very nice saturating curve. Since we have this phase where we kind of introduce explorations again and again, so you will see that the regret will rise in those phases, but the height of these things will continue to decrease. So fairly quickly, we are able to converge to what would be the ideal ideal centroidal Voronoi partition. So that is the algorithm that we had, for which we are able to characterize the upper bound on regret. We are able to show that this is order t to the power 2/3, log t to the 3. So it does not go as fast as log t. That would be very nice. Actually, I don't think we will be able to achieve log t. I think we may be able to get it down to square root t, which we have been trying to do with some success, but not yet. But our official result so far is still this is bound on regret. As t goes to infinity, we can drive it to 0. That means we are converging to the optimal coverage. And now, so far I started by the human in the loop, and I pretty much took a detour with learning. But again, I mean, as I said, humans may provide some input to the coverage where you're likely to find victims, where you're not likely to find victims, and we can again use the same multi-fidelity model and do all these things that I just mentioned to you. And we have a paper which very recently appeared in CCTA where we do exactly that. We have this multi-fidelity Gaussian process where we can have multiple sensory information and include that all together and establish very similar guarantees. So that's about search. So that's what I wanted to tell you about the search and rescue, where we identify the expertise of human and their shortcomings, and how do I incorporate that in a search problem, and then we want to extend that to multiple robots, and we want to partition the environment without knowing where the victims are, and we learn that and we deploy those guys, right? So now I want to, if I still have time, I can quickly discuss some of the other things that we do. So one of the problems, I think, as I said, I'm mostly going to talk about decision integration today, but we do some work on decision support systems. So I mean, think about a surveillance operator or a someone who screens X-rays on an airport, right? Or in the future power grids, we are thinking about humans supervising all these um, all the power demand and the supply that might be coming out of renewables and things like that. So in these problems, it is established that there's a sequence of tasks that are coming, and you need to process them, right? And then traditionally, people have done that in operational research and other communities, even in control community, modeling those as queues and thinking about how do I control the processor that does things, right? Now this becomes a queuing problem in which human is the processor, right? And then the performance function of human changes with their cognitive state, right? And there's a lot of work, which I'm not going to talk about here today, which tells about depending on the cognitive state of human, how their performance changes, right? And we can take interventions to really change that cognitive state, right? Maybe we can give recommendation to a human, okay, you need to take a short break, or and we can measure that cognitive state through EEG data or GSR data, or even sometimes through eye tracking. So depending on that, we have been doing a lot of work in control of queues where human is a server and their performance is a function of cognitive state. And can we design recommendations for the humans such that the overall system throughput is high while ensuring that the humans operate at their optimal or efficient cognitive states? So that's one part. Some of the other things that we do is an ongoing project on rehabilitation. So whenever there's a stroke, usually what happens after stroke, some of the functionalities go down, and a lot of work has gone into rehabilitation of people when you have, let's say, the arm. A lot of robotic rehabilitation work is focused on how do I gain the functionality of the arms and things like that. What we have been focusing on is rehabilitation of hand. That is a much harder problem because if you think about hand, there are, you can do this exercise there, there are 19 joints in your hand. And uh, some of the things that you get, even for healthy subjects, they are very hard to create desired motion. After stroke, there is a lot of impediment in getting this motions right. People have trouble even picking up a cup, right? So can we have some sort of robotic intervention in terms of rehabilitating the function of hand, right? So that is what we have been exploring. Can we design assistance for motor relearning for hand? So we have a soft robotic glove that we have been developing with which we can actuate these fingers. And I think on the modeling side, which is perhaps mostly my focus here, is how do we do motor learning when we have to learn in such high 19-dimensional space? For a machine, 19 dimensions is perhaps not very hard. For humans, learning something to move something with 19-dimensional spaces is a hard problem. And usually what happens is there's a lot of redundancy in the system, and there's what is called some sort of synergistic motion that humans may move all these joints together, right? It is not that I'm going to individually actuate each of my fingers, each of the joints. So there is some sort of synergistic motion that happens. So understanding how that synergies happen and can I modify them? So we've been doing some work in that domain. The other thing that I was earlier talking briefly about is the domain of agriculture. So we've been deploying some sort of mobile manipulators. This is not the manipulator we deployed. This is just a schematic picture, but we've been deploying some mobile manipulators in the farms here in Michigan State University for apple picking. And now we are thinking about when these guys are operating alongside humans, should we design the policies such that it becomes the humans are comfortable working with the robots and they understand their policies. And if robot is doing something that, for example, human does not expect, but robot knows that human would not expect this and I'm doing this, so can it offer an explanation? Or if possible, to take actions which might be equally good, but may be more expected by the human, right? So many times in robotics, we get this problem that our robots are redundant, right? And there is not just one way of doing things. So can we think about if I have, let's say, well, for redundant robot, you have infinitely many ways of doing things, but can I have some sort of cost function in their optimization that can account for what human expects us to do, right? So that is something that we are trying to accomplish, and we're still at the early phases, but hopefully in a few years I will have a better story to tell you about that. But so with that, let me conclude. So what I talked about today is a model of human decision making in multi-embedded problems. From that, I was able to identify what are the expertise of the humans. So they might identify patterns well, but the estimates might be off. And then I went on to talk about a multi-fidelity framework in which we can really leverage different inputs. If there is a human input, there is a good pattern information there. There are other biases which I can explicitly model and account for. Similar things will happen when we have these measurements coming from different modalities, from different altitudes, or different fidelity information in general. Right? Then I talked about a search problem and briefly discussed about the decision support systems that we've been working on. So with that, let me acknowledge the people who did all the work. So if you find anything wrong in the presentation, that's my doing. Anything good is because of these people. So the work on multi-embedded problem was done in collaboration with Naomi Leonard and Paul Reverdy, who was a PhD student at Princeton. The search problem was in collaboration with my former PhD student Lai Wei and Professor Shabu Tan. The coverage work was a collaboration between my former PhD student Lai Wei and an undergrad student here, Andrew McDonald. And the work that I briefly talked about the control of cues with humans is the PhD topic of my current PhD student, Piyush Gupta. The work was supported by National Science Foundation and Office of Naval Research. And with that, I'd like to thank you all for taking the time and listen to this talk. And I'm happy to answer any questions you have. Thank you.
Yeah, thank you so much, Professor Srivastava, giving us insight about the supervisory control as its application in various fields. I was just when you were describing about the EMTS algorithm, I was just wondering that in manufacturing, sometimes we do face a lot of difficulty detecting the defects of in a large, the objects, large size objects and all, where exactly the defect is located and all. So whether this sort of algorithm can be the use to the reduce the detection time. So the example which you have given, I think it has got the strong similarity with the problem statement that I'm the mentioning, and I mean I think that the sort of the algorithm will have a lot of applications in identifying defects in the manufacturing objects. So do you have anything to say on that? You are muted,
Sorry about that. So yeah, no, absolutely. There's a lot of application in that particular domain. So I think the example that I started with was ship hull inspection. And if you think about if you're trying to identify defects in ship hulls, it is exactly the same problem. Some people have tried to address that. There have been some works in that, but I think I haven't seen anything to do with multi-fidelity and things like that, or incorporating human input there. So ship hull inspection, certainly. So with some of my colleagues, I think we have thought about these problems in the context of non-destructive evaluation, which is also very similar. So once you have ultrasonic measurements or other kind of measurements, which we can deploy with robots, and we want to do autonomous search, So I think very similar problems exist. So absolutely, I think the answer is an emphatic yes. Yes.
Yeah, so I'm just giving an example just to further thinking and all. If I need to find out the defects in the painting of the cars, because that's a very critical concern for the automobile car manufacturer now. So they don't know where exactly the defect is, whether at all defect is there or not. So they need to check the entire car, car body. So whether this algorithm can help in detecting the reducing the detection time and all. So we can think.
It can. Now, the question that I'll ask here is, are there any sensing mechanisms that can be used to detect that, right? If
Yeah.
so, I think this is, so the starting point is a sensing mechanism. If I have the sensing mechanism, I can exploit the structure that exists there. Now, if it is mostly a visual thing, then I may have to train some sort of network to do that. If there are some other kind of sensory modalities, maybe I can do some sort of I don't know, ultrasound or some other kind of sensing modalities that can detect those defects in the sensory system in the painting system. Absolutely, we can do that. Yes.
So because the present days, it's mainly getting done through the imaging, for the smart manufacturing. The the for the other the problem statement that you have mentioned about the deploying different robots for the demand the function, I couldn't follow actually. My question is that if the demand gets changed with time, so how that the Voronoi partition gets changed, so that also should get changed, and then so
Absolutely.
so are you,
Uh,
I mean, is the problem that you are the solving, take into consideration about the dynamic change of the demand?
It can. We haven't done that, but it can. It can. There's a very easy modification that can be done, and we. So I think not in this context. I think in the multi-amp problem, I've been working multi-amp problem for many years. So one of the extensions that we have done there is non-stationary environments, and uh, in terms of performance, in terms of guarantees, we have to do many things there. But in terms of performance, even if I just start discounting my old observations, it would work really well. Now, the challenge really is how much I discount. And that discounting factor becomes a function of non-stationarity in the environment. So the tuning of that parameter when you discount all observations becomes a challenging problem. But yeah, I mean, as long as I know something about how much environment is changing, I should be able to do that. Yes.
Professor Srivastava, there are some questions in the chat box, so would you mind, the
Sure. Yeah.
picking up these questions? Yeah.
So DSLC is useful in case where a big object can be picked and placed by. Uh, so DSLC. So I mean coverage traditionally. So for manipulators, it's so here is how so it's in a traditional pick and place problem, I cannot immediately imagine how it can be used. uh, so traditionally the coverage control has been for mobile robots. One application I can think of, for example, that if you give me a surface where I have multiple manipulators which might be fixed but they need to paint it, right, and I want to kind of divide them to have equal amount of surface to paint, I can use DSLC kind of algorithm, right? Is it very useful? I don't know, but yeah, I can use it. But the utility really comes when it is mobile robots, and I am trying to really reduce the travel time by partition the environment, right? Uh, when it's fixed base, I don't know whether using coverage would be useful. Well, there might be application I cannot think of right now, but in general, I don't know whether coverage can be used for fixed base manipulators. There might be some scenarios I just don't know. Um, can reduce misidentification of human? That is an excellent question. So there is a, not in the first part of my work, but the part that I was talking about in the second phase, which I briefly touched about on decision supports. Uh, so as I said, I mean, a lot depends on the cognitive state of the humans, right? And that can lead to bad cognitive states, can lead to bad decisions. So when we design recommendation systems or the decision support systems, which try to um, get good cognitive states for the human, that to some extent reduces that. The other things that people have tried and to some extent have been successful is really representation of the information, right? So sometimes you may want uh, to highlight certain portion of the images. So you process the image a priori using a machine vision algorithm and then try to present it in a form that is easy for humans to identify things, right? So some of those stuffs have been done, but yeah, I think in general, there's a lot of challenges still remain there. So to some extent, yes, the answer to your question is the part that I talked about first, perhaps not, but the second piece of the resilience support system can address those problems. Is there a chance of Well, that is a very good question about misidentification due to image changes, all those things, right? Now, see, I was mostly focused on policies for the robot, so I did not pay too much attention. But I know a lot of nice work is going on in terms of creating an extra layer in the neural networks, which basically accounts for these effects of shadows, lighting conditions. And these are very challenging problems to get the deep networks to work robustly under different shadow conditions, different lighting is a challenging problem. But people have been thinking about adding a auxiliary network that can correct for these shadows and things like that. I am not an expert in machine vision, so just take whatever I'm saying with a grain of salt. But yeah, I know there's a lot of interesting work going on there. So how does real-time communication? So that is one of the challenges. So that is a very, very good question. And so if you see the application that we are working was underwater search, right? And in that case, communication becomes a really key challenge. And that is why, if you see, I had a explicit phase of communication in that algorithm. Instead of the traditional ground robots where robots can communicate all the time, I had a specific phase where there was a communication with the cloud or flooding or a base station. So typically, the way we implement these things in underwater scenarios is you have these robots, they can do the surface, and for a small amount of time they will surface on the uh, they'll surface up on the floor of the ocean or lake, and they can communicate with a robotic boat that has been deployed on the surface. So that is how communication has been handled today. Now, is that a good way to communicate? Perhaps not, but given the limitations of technology today, that is how things have been done. Do we want to do it better? Absolutely, but that is how we do things today. So I'm hoping if I haven't answered your questions correctly, please write in the chat, and I can try to see if I can change my answer. But all right. There is some electrode placement based approaches for fault detection. In this, region optimization based algorithm can be implemented. I don't know what that approach is, so I really cannot say. If you can elaborate a little bit, then maybe I can say something.
I think you have answered all the questions and all. And audience, is there more questions? One or two questions maximum, because we have already crossed the time. So if you have one more question, you can press it. I think there is no other question here. So Professor Srivastava, it was a wonderful talk. We really enjoyed, and
Thank you very much.
we are thankful that you have taken out time and then agreed to our to present the talk in our webinar series.
No, thank you very much. No, it was really a pleasure, and
we'll be connected together, and then we'll find out some the problem statements in the manufacturing domain, whether we can work together as well.
Absolutely, that'd be great. And thank you very much for inviting. I'm really glad to give this talk. Right?
Yeah, thank you so much once again for your presence.
Yeah.
Ananta, would you mind telling us the speakers for the next the Saturday? Ananta? Today there is a network issue. I can't see that one. So has it come?
No, sir. I'm sharing again.
Yeah. Please let us know the speakers.
I think, sir, is it?
It has.
Yeah. Thank you, Professor Srivastava. Please let us know the speakers as well. Yeah. Professor Suhas Joshi from IIT Bombay. You might be knowing Professor Suhas Joshi.
He taught me manufacturing processes.
Yeah, modeling, management are typical to machine materials. Then on October 16, Professor Satyendra K. Gupta from University of Southern California. So he'll be talking on the additive manufacturing and the use of the advanced robot. Then on October 23rd, Mr. Dipankar Ghosh from 3M, he'll be talking about the advanced dielectric materials and its application in the field of manufacturing. And our distinguished alumnus, Mr. Arjun Malhotra would be talking about the opportunities for entrepreneurship on 30th of October. So all the videos, of the past the webinars, all are recorded and is there in the YouTube as well. So if anyone could not attend the previous webinar, so they can access it through this, scanning this image. Thank you everybody for presence, and then I look forward to your presence in the next Saturday, 8:30 p.m. in India Standard Time. Thank you so much.
Right. Thank you.
Thank you.
Good night.
Thank you. Bye.